Good morning. The last couple of classes we've been talking about sort of an intro to biochemistry, and we talked about protein structure and amino acids on like 12 days ago now or something like that, and then on Monday, thank you. On Monday, we talked about nucleic acids and nucleic acid structure. Today will be a chalk talk, but on Friday, I'll do another PowerPoint and I'll show you some kind of neat structures that people have made using DNA, and also things that I can only show you on PowerPoint from today's lecture that I can't draw on the board because I'm not that good an artist. And then on Monday next week, we'll talk about nanobiosensors, so nanowire-based sensors, plasmonic-based biosensors, and that will lead us into a discussion of plasmonics for the rest of next week. And then in week 10, we'll talk about other types of size confinement effects and scaling laws and boring stuff. Just kidding. It won't be boring. Okay. So nanomedicine kind of evokes images of the 1960s movie called Fantastic Voyage. You might remember it as the Magic School Bus. If you're a little bit younger than that, or maybe around the same time, you'll remember a couple episodes of Futurama. The problem with shrinking stuff down, though, is that are the atoms being shrunk? Because if the atoms are not being shrunk, then how are you going to breathe an oxygen molecule that's like 100 times bigger than the hemoglobins? But anyway, I digress. Why should we bother with? Uh-oh, it says I'm disconnected. We're good. Why should we bother with nanomedicine, nanostructured particles for drug delivery? Well, the case where nanomedicine is most useful, perhaps, is in cancer therapeutics. So cancer is the second leading cause of death in the United States. There are about 600,000 deaths per year, and that's second only to cardiovascular disease, around 620,000 deaths per year. There are about 1.7 million new cancer diagnoses per year, and everybody in this room has been affected by cancer in themselves or in a loved one. So there is obviously a reason to explore new ways of treating cancer. And just to put that into perspective, it's about the number of fatalities per year for cancer about 20 times auto accidents and gun deaths that are around 30 to 40,000 per year each. So more than an order of magnitude greater destructive potential in terms of human life. So cancer, as we know, is treated with a couple of types of interventions: surgery, radiation therapy, and chemotherapy. Now, all of these modalities of treatment tend to affect healthy tissue as well. So one of and in particular, chemotherapy drugs, you ingest or get injected with a drug that's just either a small molecule or a protein, and you don't have control over where it goes. You don't have control, so it's going to healthy tissue too. Suppose it interferes with cell division, it will interfere with cell division in the healthy cells too, and it will go all over your body. Another thing that there is that is problematic is that cancer drugs can be, many of the small molecule ones are hydrophobic, so they will aggregate once they're in the aqueous biological milieu, and what they can form is an embolus, which is a solid packed bit of solid material that can travel through your blood vessels and occlude blood vessels, so you could get a stroke or an infarct in one of your organs, or a stroke if it's your brain. So there are a number of strategies that one can use using nanostructured materials to address both the issue of targeting, so localizing the therapeutic, but also to the cancer tissue, but also to control the release rate in the biological environment. So if you take a drug, or if it's injected, it has a profile that kind of looks like this, and then it goes down over time. Now, the rates of tumorigenesis can follow a diurnal cycle. So a tumor might grow more rapidly at a certain time of day, depending on your sleep schedule and and the meals and so on. Just like we follow a circadian rhythm, which is the origin of jet lag, so do tumors. So it would be nice to be able to time when the drug is released, and in other cases it might be desirable to have a more or less flat distribution or a release profile in the body, so that you're not going in for the treatment and it's like this, you go home, then it's like this, then you go home, then it's like this, and so on. So you want to be able to use nano-engineered devices in the form of particles in order to target, to evade detection by the immune system, because a foreign body is going to be removed by the immune system, and also to control the release rate. And there are a lot of ways that one can think to do this, but I just want to write down a couple of characteristics of cancer drugs. And these are general characteristics. This isn't always true, but we have poor water solubility, lack of targeting, non-specific distribution, systemic toxicity, and you can see these are kind of different ways of implying the same thing, except for this one, and low therapeutic index. Therapeutic index, there are more and less sophisticated ways to talk about the efficacy of a drug, but basically it's the concentration that is beneficial versus the concentration that's harmful. So in animals, we call this the LD50 over the ED50, and this is the lethal dose for it's the median lethal dose. So this is the 50 means the 50th percentile. It will kill 50% of rats. This is usually in concentration in the blood, so grams of the drug per mass of the drug per mass of the organism, and this is the effective dose. Where one starts seeing therapeutic potential. And in humans, we don't do the trials such as to kill 50% of the human trials of the human subjects, so we call it the toxic dose over the effective. This is the median toxic dose, and this is over again the effective dose, and this is animals here and humans here. Okay, so what are some characteristics that we would like to, well, some properties that we would like to engineer into drug delivery nanoparticles? One is to increase the water solubility. Prolong circulation before it's filtered out by the spleen or kidney or phagocytes, white blood cells. Improve the biodistribution. And reduce the immunogenicity, that is, reduce the immune response. And what are some techniques that one can use to take a nanoparticle that would ordinarily be targeted for removal by one of the body's many mechanisms that can remove foreign matter, and to get the body to not respond in that way. We find that there are many different ways of targeting. So as the nanoparticles are circulating through the system, we don't want them to be active everywhere. So what if we only want them to be active when they're in the tumor, for example? And we can do this passively. And I'll just give you a few sort of archetypal ways. One is the pH of the tumor microenvironment. So the pH of a tumor is about half a pH unit, roughly lower than the physiological pH of the extracellular space. We can exploit the leaky vasculature. So when a tumor is built, it was done using it's done like using a handyman job, like very poor quality plumbing. So the vasculature leaks from the blood vessels into the tumor, and also the drainage is not good to the lymphatic system. So stuff goes in, tends to accumulate, and this is actually called the enhanced permeability and retention effect, or the EPR effect, and we'll talk about this in a bit more detail later today and also on Friday. And also we can target using overexpressed proteins. On cancer cell surface, on tumor cell surfaces. So a tumor cell is unlike a healthy cell in a lot of different ways, and sometimes a certain protein will be expressed on the surface, and if we have an antibody that is on the surface of the drug delivery nanoparticle, it can selectively adhere to, or selectively bind to the cancer cell, and then we can somehow induce it to release the drug, or maybe there could be some sort of automatic mechanism that is used to release the drug. Okay, so what are some examples of actual nanoparticles? Say there may be more, but you can generally fit most types of drug delivery nanoparticles into three general classes. We have nano shells, where we have a core, which can be, say, silica or hydrogel. Could also be aqueous. And then we have a shell, which could be a metal. It could be a polymer. This could be an enzyme-sensitive polymer that could be chewed up by an enzyme, hydrolyzed by an enzyme to release the target, or the cargo. Could be some other kind of porous shell, could be like an oxide. Or if the pores are small enough, we can control the rate at which the drugs are released, almost like a wiffle ball, one of those plastic baseballs that has holes in it that's really makes it really easy to throw a curveball. Another class we've met already, and that is the liposome. Certainly the most commercially successful so far type, or therapeutically and commercially successful so far type of nanoparticle therapeutic, where this is basically a bilayer vesicle of amphiphilic molecules that can take up drug molecules if you prepare them in the right way. And the interior is aqueous. The exterior is aqueous, and the inside has stuff, can fit stuff that's, that is the interior of the bilayer vesicle, and the interior of the skin can solubilize stuff that's hydrophobic. So we can actually use a liposomal particle to solubilize either an aqueous or a hydrophobic, so either a hydrophilic or a hydrophobic type of structure. There's a question in the front.
No, I just want to look at the diagram a little closer.
Okay, we're cool. So this is the hydrophilic head groups inside and outside, and then the hydrophobic hydrocarbon groups. Another type is a polymer nanoparticle, where we take polymers like the ones we've been talking about. So polymer-based nanoparticles. That could either be water-soluble or not water-soluble, but swellable enough by water to allow slow release. And there's another type of polymer nanoparticle that is starting to work its way into into clinical trials, and that's based on dendrimers. And dendrimers are three-dimensional polymers. I should add that this is a good time of the course to go to Cody's office hours because he knows 100 times more about nanomedicine applied to cancer than I do, because he did his BS and MS research on this topic. So just a little shout out to Cody. All right, let's talk about these types of particles and some of their key characteristics. How about nanoshells, where the shell is a metal? So there's a technique that's under investigation called nanoshell-assisted photothermal therapy. Or NAPT. North American Partnership Trade. Sure. This is a cancer cell, not drawn to scale. And what we're going to find is that there are proteins that appear more frequently on the surfaces of cancer cells than on healthy cells. So these are overexpressed proteins. Overexpressed cell surface proteins, which behave as the antigen. And suppose we have some nanoshell nanoparticles that have an antibody. That is an anti-overexpressed protein antibody. So it binds to the surface. Let's say we're successful here and we bind some nanoparticles to the surface. So the metal shell, if we shine light on it, there's a very useful nano-confined effect called a plasmon resonance, which is when a metal nanoparticle with a certain dimensions will have its electrons slosh back and forth in resonance with a particular wavelength of incident light. And it only occurs in nanostructured surfaces at metal dielectric interfaces. So if you shine light of a particular wavelength on a metal nanostructure, you can induce the electrons to slosh back and forth in resonance, and that leads to greater scattering at those frequencies and can also lead to heating up of the environment. So you can see where I'm going with this. So the metallic shell resonates with near IR light Are we okay with H nu as the symbol for light? Near IR light and heats up. So as the energy of the plasmon resonance dissipates, it dissipates in the local microenvironment, and you can get maybe like a 40 degrees Celsius increase, which is enough to kill the cancer cells. Another thing it can do, let's say this is one option. Another area of exploration is actually to use the plasmon resonance to melt or break holes in the metallic shell. And if there's a drug inside, it could release the drug. Question, yep.
It's kind of twofold. So how, what's the factor of how much more the protein's expressed in cancer cells than just regular cells? Is it significant?
So the question is, how much more is a protein on a cancer cell surface overexpressed? It totally depends on the cancer, but it is significant. Do we know a order of magnitude? Yeah.
Okay. So. And then the second question is kind of based on that. Then is this targeted in the sense that you irradiate the region where you like where the tumor is? Mm-hmm. Okay. So then it's not necessarily used for like stage 3 or stage 4 treatment in that sense.
You would only irradiate the tumor microenvironment.
Okay.
Yeah.
How much do the nanoparticles heat up?
In the range of tens of degrees Celsius over the baseline physiological temperature of 37. They're also easier to melt when they're confined because nanoscale structures have melting point depression, and the reason for that is that it takes a certain number of metal atoms in a nanostructure in order to achieve the bulk melting temperature. So if you have just a layer of 2 or 3 atoms deep, these will be thicker than that, but if they're just 2 or 3 atoms deep, then we don't have enough metallic bonding to reach the local melting temperature, so we can have a really significant melting point depression. Yeah.
So depending on whether we want the first or second method of action, we use, say, a thicker wall for something we wanted to achieve like a thermo kill versus something we wanted to degrade, or do we use different metals and frequencies instead? Like, is it a structural difference, or do we use different compounds?
Both. So this is, we wouldn't be doing this using the same type of nanoparticle at all. We would want to pick a thickness that resonated at, say, the near IR wavelength of, I think, 800, a low 800 nanometers in the near IR regime. If you just want to, I mean, you would want them to resonate in both cases. You would want to have the thickness tuned to the peak output of the IR source. Does that answer?
I'm just curious, like, what would if we wanted to produce localized heat to kill a cell versus actually degrade? I mentioned the heat to kill a cell would be a lot less than the heat necessary to melt a metal. Or am I mistaken?
No, that's well. There are some subtleties here, but you're right. It would take less heat to kill a cell, but it takes a surprisingly small amount of heat to put a hole in a metallic thin film that has a defect in it already.
But it probably could kill more with its contents than just an individual cell it was contacting, right?
I don't know. It depends on what the system is. Yep.
So when you're talking about all those approaches for nanoparticles, are you saying it because if you're in
if we're bound to the cell, then the point is to bind the nanoparticle to the cell, then heat it up, and then it kills the cell that it's bound to.
And then, why are we using in particular nanoparticles? Is it because when we were talking about the normal chemotherapy and all this kind of stuff, there's no enough dosage that goes to cancer cells, but when we're using nanoparticles, it's like targeted also, like usual drug will kill them.
Correct. So like Taxol, one of the most famous examples of a cancer drug for ovarian cancer, breast cancer, lung cancer, there's no space to put an antibody on it to target it to a cancer cell. It just goes everywhere. You lose your hair. It can damage your liver. It has a very low therapeutic index by itself. But this is only one type of maybe 100,000 papers that have been published on anti-cancer therapeutics. So we have a lot of space to explore here. How about liposomes? The generic sort of way that we can think about making a liposome is to start out with a lipid dissolved in an organic solvent. And the drug, which are all sort of dispersed here in a homogeneous solution. Then we evaporate down to get the solid material here. So this is our residue. Then we redisperse it in water. So we have evaporation, then we add water to redisperse it, then we have our liposomal drug suspension. And if we have a hydrophilic drug, it will reside on the interior of the liposome. And we'll get a faster release rate than if, because all that we have to do is sufficiently agitate the liposome to break a hole in it, even transiently, for the drug to escape. But the bilayers will still persist for quite a while longer. If we have a hydrophobic drug, it resides in the inside the lipid bilayer. And we have slower release. The reason we have slower release is because it requires the destruction of the entire bilayer structure, not just a perturbation of the liposome to transiently break holes in it, but rather to bust it apart and then bust apart the busted apart bits in order to release the drug. How about polymers?
Really quick, Professor?
Yep.
How are these ones targeted? Or targeted towards cancer cells?
You can have transmembrane domains in a lipid particle. You can have something that's grafted to the surface of a lipid particle. You wouldn't put it on every lipid molecule, but it could be something that that would bind to a cell surface. But it also, in sort of a basic type of formulation, you could solve the lifetime problem of a drug or the controlled release problem of a drug, but not necessarily the targeted aspect of the drug. So you still get something even if you can't target it.
Yeah.
So how about polymer nanoparticles? You can imagine a couple of different ways of doing this, depending on what your starting material was. You know, if it's a blue sailboat, you might get something different from it. If it's a red house, that made no sense on the audio-only podcast. You know, we could have a core shell type of particle that had a leaky shell, just like we met before. But in this case, we have a polymer shell. So in this case, it's diffusion controlled, where the drug molecules represented by these dots in the interior are diffusing through the barrier, and this is an insoluble polymer. Which could be some acrylate or something, probably an insoluble hydrogel. You can also have a solid structure of polymer. This could also be a hydrogel particle, where you have drug molecules in the interior. And again, you have also diffusion controlled. But you could also imagine an erosion controlled mechanism where, say, this was a water soluble polymer. Where this particle is dissolving by erosion, and this could be some kind of hydrolyzable particle. And one of the most famous examples is a polylactic acid, which you can hydrolyze at physiological pH. So, what is the goal? The goal could be to match the release rate with the rate of elimination. How are drug delivery nanoparticles eliminated? Well, in the case of erodible ones, it's no problem because they are dissolved into products that you might find in the bloodstream anyway. For super small nanoparticles, like particles that are less than about 8 nanometers, they are filtered out by the kidneys and are excreted through the urine. In some cases, you have particles that are larger than, depending on the surface chemistry, and there's a big field here, but depending on the surface chemistry, you can actually have them degraded in the liver and sent to the gallbladder to be eliminated as bile. But unfortunately, for insoluble particles, a very common fate above 10 nanometers is to just get stuck in the liver or the spleen and never leave. And this is particularly the case for metallic nanoparticles, but insoluble polymer nanoparticles have this problem as well. Sometimes we have a problem of burst release of physisorbed drug molecules on the surface of a drug delivery nanoparticle. And a typical erodible polymer is PLA, polylactic acid. And you don't have to memorize this structure or anything, but this bond between the carbonyl oxygen, the C double bond O, and the O, this is called an ester bond, and it's susceptible to hydrolysis at physiological pH. Oftentimes, if we have a polymer that's erodible, it's also going to have diffusion controlled erosion, diffusion controlled release as well. So it's hard to separate these mechanisms if you have something that can be hydrolyzed. Yep.
Can you elaborate a little bit on what you mean about burst release through the drug? Is that like something we're trying to avoid, or is that a phenomenon that occurs?
Burst release is something that is not desirable. So burst release is, say you have some polymer nanoparticle and it's difficult to control during the synthesis. That's loud. Difficult to control during the synthesis whether the drug molecules end up in the interior or on the surface. So say you have a bunch in the interior, but then in the process of synthesizing these nanoparticles, you also end up with a bunch that pepper the exterior. Now, when you release this into the biological environment, all of these are going to come off first, and they come off all at once. So your drug release profile, what you want is perhaps something that's flat, and what you end up with is something that looks like that. Yeah, there's a spike at the beginning. So a dendrimer is a type of special class of polymer that has a core and branches. It's like a three-dimensional three-dimensional polymer that ends up giving you a nanostructure. So let's say we start with the core and we react it with a 3 times a branch structure, and the prime means that it's protected. So A reacts with B, but nothing reacts with A prime until we get rid of the prime by deprotecting it. So in the first generation, we can imagine that we have A, so this is the core, and then it's reacted with the branches, all terminated in A prime. Now we need the prime because otherwise these would react with themselves. So this is called generation 1. Then what you do is you deprotect and you add. Now we add 6 times the branch. And you end up with something that looks like this. This is fun. Okay, then you have A primes all around the periphery. And if you do this enough times, you end up with a monodisperse, that is to say, a structure that's not disperse at all. This is a way of generating, using synthetic chemistry, something that has the properties of a polymer, but which is monodisperse. And it gives you this automatic porous structure where you can prepare these in the presence of a drug molecule. And these are for storage of drugs. It's how you smuggle drugs into the system. Other ways of smuggling drugs into the system, perhaps you could use polyethylene glycol. I know I said never to call it polyethylene glycol. Use polyethylene oxide, but it's always called polyethylene glycol in this context. So you pegylate the surface, and PEG has a characteristic that it's not targeted for removal by the immune system as readily, although a good fraction, like a quarter of patients, will actually develop antibodies against PEG to remove these structures. And another technique used by Professor Zhang at UCSD is to use red blood cells. So you take the red blood cells and you bust them up, and then the cell surface proteins on the proteins and the lipid layer, the membrane will actually reform around polymer-based nanoparticles, and then your body thinks that there are little red blood cells floating around, and then they can go around with impunity wherever they want in the biological system. So I'll elaborate on these topics on Friday when we'll have a PowerPoint presentation with some nice images. So thank you very much.